This video will serve as an introduction to equipotential surfaces. So we're going to start out with an electric field here. And we know that it doesn't take any work to move a charge perpendicular to an electric field, which means that the voltage level along any line that is perpendicular to an electric field is going to be the same. We can also solidify this idea a little bit more if we take a look at how we define voltage difference. So one of our equations is that voltage difference is equal to the electric field times the distance that is parallel to the electric field. So if we do not have a parallel component here, if we do not travel any direction in the same direction as the electric field, we know that the voltage difference is going to be 0. So each line that I've drawn here is perpendicular to the electric field and is going to have the same voltage level along these lines. So they're all each individually going to have their own voltage levels, but the voltage level at any point along that line is going to be the same. And these lines are called equipotential surfaces. So the last example that we just covered showed what some equipotential lines could look like for a uniform electric field. You could also be asked what they could look like for electric field lines that come out of a charge, like here. And we know that equipotential lines, or surfaces, must always be perpendicular to the electric field. And the only way that this is possible is if the equipotential surfaces were circles in 2 dimensions, in this 2-dimension representation, or they could be spheres if this were a 3-dimensional or real-life representation of the electric field lines. So notice how the equipotential surfaces are still perpendicular to the electric field lines. We know that the further down in an electric field we travel, the smaller and smaller the voltages become. So our voltage levels decrease as we move further away from the charge. And just to be clear, these voltage levels would be the voltage level throughout the entire equipotential surface that is represented with a circle here. Equipotential surfaces can also not be as uniform and pretty shapes like we've seen in these last 2 examples. So if we have a few scattered charges here, the equipotential surfaces can become oblong shapes. All right, they can also have voltage levels that are not necessarily nice numbers either. So let's do an example. We want to label the electric field vectors at the given point. Remember that electric field vectors are perpendicular to the equipotential surfaces. The lines that are given above have voltages labeled beside them, so we know that they are equipotential surfaces. Therefore, the electric field lines either have to point essentially up or down to be perpendicular to these surfaces. We also know that electric field lines point towards lower voltages. So we know that our electric field lines are going to point down because our lowest equipotential surface has a voltage of -5 volts, or the smallest voltage. And we know that these electric field lines are going to have to point at a right angle to the surface. Next, we could be asked to calculate the work needed to move a 3 coulomb charge from C to B. So we know that our voltage difference equation is equal to delta V equals the work divided by the charge. So it's the work that it takes to move the charge. So since there is no change in voltage, right, we know that we do not have to actually exert any work in order to move this charge. So remember that if you ever are moving a charge along an equipotential surface, it takes 0 work to do so. And lastly, we're going to be asked if a 4 coulomb charge is released at point B, what is the kinetic energy when it reaches point A? So we have our voltage difference equation, and we know that work is equal to the change in potential energy, and we also know that potential energy is gain or lost at the expense or gain of kinetic energy. So we can plug in our initial and final voltages and the charge, and we see that the change in kinetic energy is 30 joules. And this makes sense because the positive 3 coulomb charge would gain kinetic energy since it is moving towards a lower voltage level, which is where it wants to travel.